the last thing we had shown was that the closed loop gain, okay, of our system was going to be related to the ideal. So we had defined what that ideal was. And but how close or how much we deviate on our real closed loop gain from the ideal was given by this factor. Where A beta is the loop gain. Not the same thing as the closed loop gain. A sub f is the closed loop gain of the system, what we really care about. But A times beta is just the loop gain because it comprehends the forward gain and the feedback network gain beta. So I just wanted to show a small example of how much the closed loop gain varies with respect to the ideal one. With, let's say, just a loop gain of 100, which is not, it's reasonable. And if you do that, you can see that this factor here, okay, that factor, you know, becomes 0.01, okay. So essentially you get this factor to be 1 over 1.01, so very close to 1, okay, very close to 1. So this is very close to 1, not quite 1. So the point here is that since this is large, this factor tends to be very close to 1 but less than 1, and the point is that your ideal never gets reduced too much in terms of what the real closed loop gain is, and that's a good thing, okay. Let's look at other relationships that we can write, okay.
Professor?
Yeah.
Going back to what you just ended on for the closed loop ideal gain, when you said AB is high, when you plug it all in, the denominator is going to be slightly larger than 1, and you said AF is going to be reduced. I just got a little bit confused because it never, you were trying to say it never gets greater than 1 or up to 1.
Yeah, so let's unpack that. So specifically, and if A beta is 100, then this factor over here, that's going to be 1 plus 1 over 100, okay? So this here is going to be 1.01. So the whole thing is going to be less than 1, right?
Yes.
So are we saying the same thing?
I think so. Was there a significance of it being close to 1?
Yes, because what we're saying is that this factor, this whole factor that is less than 1 but almost 1 reduces the ideal gain we're saying and we're demonstrating that the real closed loop gain is always less than the ideal, but very close to it because of the nature of the loop gain.
All right, that clarifies it.
All right, great,
Thank
awesome. All right, so let's look at some other relationships that we can write, okay? Because they may become useful later on. And this business of feedback, these formulations that we're making are a bit abstract, but you have to be very comfortable with them because you need to apply that to actual circuits and how we sample the output and how we couple that feedback after the network into the input. So be thinking about actual transistor circuits where this is going to be happening. So it's, we're drawing boxes and so forth and writing these relationships, but really we're going to get to the point that we're going to be applying it. And if you're not comfortable with the simpler abstraction, then you're going to have issues applying that to the actual circuits and seeing that. So let's look at some other relationships. So one is that the feedback signal, okay, can be written as A beta 1 plus A beta times the input signal, okay, and the error, so we had defined X of I as the error, is 1 over 1 plus A beta times the input. And these are useful relationships, and these fractions are actually transfer functions, okay? So let's talk a little bit more about the loop gain and some of the its characteristics. So that is the definition of loop gain, is A times beta, essentially the transfer function of the forward part of the system, A, and then the transfer function beta of the feedback network. So some characteristics that are important about that loop gain. So the sign of the loop gain determines the polarity. Of the feedback. The loop gain must be positive. Okay? Must be positive for the feedback to be negative. Okay? Because the whole system is formulated on this concept that you are generating from input to the error. You are generating this error as the difference of the input and the feedback. So for the feedback to be negative, this has to be positive, the loop gain. Question? Is that a question?
No, no question. I'm just talking.
Okay. So that's important to keep in mind. Okay? One more characteristic. The magnitude of the loop gain determines how close the closed loop gain is to the ideal closed loop gain. And we just went through that. Okay? Also, the loop gain determines the amount of feedback which is 1 plus the loop gain, and as we will see, and the improvement on certain quantities and characteristics of the system, and the improvements due to this feedback mechanism.
Dr. Hernandez?
Yeah.
Can you go back to the first characteristic real quick?
I can read it. Once the drawing is gone, it's gone.
Oh, okay.
Yeah.
All right, that's fine.
There will be a video of it, okay?
Mm-hmm. Okay, thank you.
Yeah, there will be a video. All this is being captured. But no, I mean, it's real time on the pad. So once I have to clear the pad to keep writing. So sort of erasing the board. Same thing. All right. So the loop gain. This is very important because the loop gain, remember, these are circuits. So the loop gain varies with frequency. It's not a constant. These are transfer functions. And you know, if it varies with frequency, it can cause the overall closed loop gain to have undesirable properties. Okay, so for example, if the phase of the loop gain is 180 degrees, meaning that the sign of the loop gain is negative, then the error, because the way that you couple is subtractive, then the error is always greater because you're always adding. So the error is always greater. So another way of saying that is that feedback becomes positive. And if you have positive feedback, that means instability. Okay? So a very important note, very important note, need to we need to make sure that the frequency behavior of the loop gain is such that the system is stable. Okay, that's very important. Okay, so all these sentences are such that you get an appreciation for how important that loop gain quantity is in aspects as important as the stability of the system. So how much this loop gain can influence these important characteristics. So if it is an important quantity, we need to be able to determine it. Okay, so let's talk about how do we determine the loop gain. And let's go back to our system that we drew, that, you know, basically our model of the system. So this was our system, and we want to figure out and if you can visualize your system as such and identify the output, the input, then you can figure out the loop gain of the system. The first thing is that we're going to set the input to 0. Okay? So now that is this input is 0. So what we have out of this box here is just an inversion, because it's 0 minus the feedback signal. Then we need to break the loop. The best place to break the loop is right there. Okay? So we can break the loop there and denote what is going into the feedback network as x of t, and what is coming out of the forward path x of r. So now we have two distinct nodes, and we can determine the loop gain as the ratio of x of r over x of t, where this becomes an input to the loop. This becomes an input to the loop, and this becomes the output of the loop. So we want x of r over x of t. Okay? One observation is we have the assumption here to be able to break the loop in this manner is that the beta network does not load down the A network. okay? Because if he loads it and you break the loop here, then you change the characteristic of the whole thing, okay? So what that means is that A must have a very small output impedance relative to the input impedance of beta, or saying the same thing in a different way is that beta has to have a high input impedance with respect to the output impedance of A. That's very important. So let's just write that down somewhere. So the beta network cannot load down a network. All right. And then what we're going to do is apply x of t as an input and determine what x of r is, and take the ratio. Okay. So if you look at this picture, what you can write is that x of r is equal to minus a beta x of t, and therefore a beta, which is the loop gain, is minus x of r divided by x of t. Okay. And in our formulation, the nice thing is that there is this negative sign, which confirms for us that we have a negative feedback system. And negative feedback is what is mostly used, is a good thing. That's the type of the good feedback, at least in this context. Okay. Now let's look at some the ideal case, because one of the things that we have said is that the forward gain A for op amps, for transistors, it tends to be really high. Okay. So what if we look at the extreme case where that gain is infinite? Okay. So let's look at that. If we look at that, back in, in our original drawing, I'm going to be drawing this many times for the foreseeable future here. If A is infinite, okay, if A is infinite and I'm getting something out of it, I can get something out of A, the A network, even if the error is 0, because A is infinite. Now you're already familiar with this concept. This is exactly the concept behind the virtual short paradigm in op amps. The gain, the A gain of op amps is so high that actually, and remember these are linear systems, for the op amp to behave linearly, you have to have both inputs be very, very close. Otherwise you get distortion and you get no linear operation. Well, this is sort of related to this. We're saying the error or the difference, which is the same thing, the difference between the inputs of an op amp is zero because the gain of the op amp is so high. Okay? And what that means is that the feedback, because the error needs to be zero for the system to be linear, the feedback needs to be the same as the input. To do that, for that to happen, the output needs to be 1 over beta times the input. And if we look at the definition of the closed loop gain, which is the output over the input, we get that is 1 over beta, which is equal to the ideal as we defined it. So what this says is that if A is really, really high, ideally infinite, then we get our ideal closed loop gain. So that makes sense. Okay? Now at the same time that having a high gain is desirable, it also has some negative effects. Mainly if it varies all over the place, which it tends to be in real components. Okay? And luckily, the nice thing is that since we can use feedback to make our system less sensitive to that gain that we want high, but also is varying widely, we can use feedback to desensitize that gain. We can make our circuits useful. So let's look at that property of the negative feedback in terms of making our system less sensitive to the high gain. So one important thing is making the circuit less sensitive to the gain. And if we formulate our closed loop gain as such, and if we want to see how sensitive the closed loop gain is to the open loop gain A, and what I care about is the closed loop gain. If I want to see how close, how sensitive one quantity is to the other one, what I do is I differentiate. So with respect to the open loop gain. So if I take the derivative of this expression here with respect to A, I get this expression, okay? And then what that means is that a change in closed loop gain relative to a change in the open loop gain is going to be reduced. Or in other words, the change of the open loop gain is going to be reduced by this factor to give me the change in the closed loop gain that I get and that I care about. So another way of looking at that as a percentage, so let's look at a percentage, a change in closed loop gain by the total closed loop gain is equal to this factor of the change as a percentage of the open loop gain in terms of the overall loop gain. So if I have a change in open loop gain, it's going to be reduced by this factor to get me the change in the closed loop gain, which is what I care about. So this is called the sensitivity factor. And as I said, think about how useful that is. Because there is nothing that you can do. I mean, things are fabricated, things are manufactured, they vary. There is variability in physical products. This can be large. But because of the feedback introduced, specifically the negative feedback inherent in this expression with the help of the feedback network, that change here is reflected much less in the actual change of my system, which is the open loop, the closed loop gain, which is what I care about. So that this is a very useful result and shows the usefulness of negative feedback. And that's where we're going to stop today. Next time we'll start talking about other useful uses for negative feedback, namely bandwidth extension. We'll do that a week from today. So thank you very much, and have a great weekend, okay?